Hi everyone and welcome back to PrepFusion. I'm Anish and today we will start with the lecture 21 of our this machines subject. So today we will discuss about parallel operation of transformers and why parallel operation is important. Okay. So let's take an example. Let's take a single phase transformer and I have this 200 volt here 10 kVA transformer and it is supplying a 10 kilowatt load at a unity power factor. So what is the kVA rating? kVA rating is 10 kVA. So if I close the switch here for this for this load, then no problems. It will be able to supply the power, right? Because this is rated at 10 kVA. Now, if another load is there, and then if I close the switch here, what will happen? Will this transformer be able to supply the power? No, it will not be able to supply because its rating is 10 kVA only. So what will happen? Like this load also will get some power, this load also will get some power, but the power will be something divided. It will be half, something like that, right? So I will not be able to give the full power, right, to all the loads. Okay. So the problem, what is the problem? That is the problem, right? This is the problem basically. So I cannot actually, I cannot actually basically I cannot actually use this. So how can I use this? How can I use this actually? Like how can I use it? To use it, what we need to do, because we have to increase our capacity of the supply. How can I increase my capacity of the supply? We can connect two transformers in parallel. Okay, so that is what we are doing. So we will connect two transformers in parallel. So this first transformer has a kVA rating of 10 kVA. Second one has a same kVA rating of 10 kVA. Overall kVA rating of the whole system will become now 20 kVA. So now I will be able to service 20 kVA of load. So this is the main purpose basically. The main purpose is to service the load, because in your homes you see there is a distribution transformer, and of course you have your own home, you have your neighbor's home, that guy like Sharma ji ka beta, that guy. Okay, so all these people are there. Okay, this, and all of them turn on the light at once. You would not want like your light to be dim. If I use this system, then my light will be dim. Why? Because overall I will not be able to supply the power. So ultimately voltage will drop, and if voltage drops, light will not be able to light up properly. Okay, so that is the thing here. That is the thing only. Okay, understood. So here I have two transformers in parallel, so I am able to overall kVA of the system will be 20 kVA. So I will be able to service 20 kVA of power. Got it? I will be able to service 20 kVA of power. Okay, so now this is my basically the crux whatever I have been discussing. So parallel operation of transformers means connecting the primaries to a common source and secondary to a common load, allowing them to share the total load. This is essential in system where a single transformer cannot handle the entire load efficiently or economically. Okay, so why use parallel operation? So parallel operation, first of all, first point is enhanced load capability. Of course, we will increase our load handling capability, improve reliability. So even if this transformer, let's say this transformer has failed, right? Then if the load is 10 kVA, then this will be able to service the 10 kVA, even if this has failed. So, but here, right, if this has failed, right, I will not be able to service at all any load. But yes, I do agree. But if this transformer has failed, you will say, sir, you will not be able to service 20 kVA. No, these two loads, if they are connected, I will not be able to service 20 kVA. Yes, you are correct. I will not be able to service 20 kVA. But at least if this transformer is gone, at least I can at least service this load, right? This is at least a possibility. Okay, this is at least a possibility. So at least something is going out, right? Nothing is better than something, correct? So that is why it is written here, improve reliability. Operational flexibility. So during off peak hours, some transformers can be turned off to reduce no load iron loss. So if maybe during low peak hours, right, if only 10 kVA it is asking, so uh, uh, what you can do is basically you can turn this transformer off. Let's say like all these transformers work 24 hours a day, right? If I give this transformers enough time, like turn it off, so it will be cooled, so it will perform much better, it will be much efficient. Next time I will turn it on. So 20 working any device 24 hours, right, it will automatically can get damaged or there will be wear and tear, right? So same like you, if I work 24 hours continuously, I will not be able to be efficiently working, right? The efficiency would not be there. Same here, right? If I just keep all these transformers on for 24 hours, it will not be efficient. So that's why maybe during low peak hours, maybe I will keep this transformer on and this transformer off, and then again I can swap these two. Okay, so that is the operational flexibility. Cost savings. Smaller transformers are easier and cheaper to maintain or replace. Also, a full size standby transformer isn't needed. What do I mean? So building a 100 kVA transformer might be very expensive. Okay, single unit 100 kVA transformer. So maybe it will be better if I build a like what do you can say, 4 25 kVA transformer. If I build 4 25 kVA transformer and connect them in parallel, that will be cheaper than building a single 100 kVA transformer. Also, like, there is very less reliability, right? If this transformer for some reason gets damaged, whole 100 kVA is lost. But here, even if one transformer is damaged, 75 kVA is still there. Okay, that is why cost saving. So now let's come to few conditions for successful parallel operation. So we will discuss about this. Okay, don't worry. One by one we will discuss and prove why are this required. So there are two types of condition. One is essential condition. Okay, essential means it is mandatory. It has to be satisfied no matter what. Okay, first essential condition is there must be same voltage ratio. Why? I will explain. And they must be connected in the same polarity. That's why the polarity test is very important. That's why we learned polarity test. Okay, I will discuss one by one each of them. Now there are two conditions which are desirable. First one, desirable means for better performance, for optimal performance. But it's not like if this is not satisfied, my parallel operation will not work. No, parallel operation will work, but for optimal performance I will want these to be satisfied, like identical per unit impedance. So per unit impedance, whatever is the transformer per unit impedance, both of them should have same per unit impedance. Why? I will explain. Because then the load sharing also will be same. They will share according to their per unit impedance. I will discuss that, don't worry. And their x by r ratio must also be same, because if their x by r ratio is not same, the power factor, right, they will not be able to operate. Both the transformers will not operate in the same power factor. Maybe there will be a reactive power exchange between the two transformers. How it happens, all this I will explain. Okay, so let's first come to the this condition, same polarity. Why they must be in same polarity? As the name suggests, if they are not in same polarity, there will be circulating currents. Why? Let's take example. Okay, this is the example. So here I have E1 is connected here, but here I have E2. So E2 are actually connected opposite fashion. So this will develop a voltage. Let's assume this will develop a voltage plus minus E2, because they are in parallel, same voltage only, and this will develop a plus minus voltage E2. So if I assume a small resistance between these two transformers, okay, if I assume a small resistance, like very small resistance E2, if I apply a KVL in this loop, like this we have already previously discussed, right? If I apply a KVL in this loop, what will happen? If you see that this will be 2E2 equals to I circulating into R, where my I circulating will be 2E2 divided by R, and R is just a winding resistance that will be very low. Okay, wire resistance that will be very low. So I is very high, very high, right? High. And this is very dangerous. A high circulating current is flowing through the winding that can damage the winding. Okay, damage the winding, because my winding is not rated for this high amount of current, right? So that is the problem actually. That is the problem. Okay, so that's why they must be connected in the same polarity. Pretty easy and obvious to understand. Okay, I don't feel this is much difficult. Reason is given here, circulating current will flow, it will overheat and all those things. Okay, now why there must be equal voltage ratio? Why there must be equal voltage rating? Okay, if they are not rated, if their primary are not rated in the same voltage, there will be a problem. Again, there will be a circulating current. Okay, so let's solve one by one. So my supply will be one single supply only, right? Let's say this Vs. Okay, and this transformer 1 is rated for value plus minus Vs1, or Vs1, that is Vs only. And this second transformer, if I connect that in parallel, this is dot. Okay, let me take this as, let's say, some weird number, let's say some VS2. Okay, now if they are of different voltage ratings, what will be the problem? Same problem, a circulating current will flow, right? I will connect the dot to dot and I will connect the non-dot to non-dot. Again, if I assume a resistance here, small winding resistance here, again if I see that this value will be what, if I apply KVL in this loop, like I will start, this is dot, so I will start from here, use a different color, I will start from here, I will go here, here, and I will end here. Okay, so basically I will start from plus VS2. Okay, I will start from plus VS2, then this will be minus VS, then small resistance, right? Small resistance, so drop will be like this only. Okay, I missed the drop, I had to write the drop as well. So plus IC into R minus Vs will be equals to 0. Okay, IC equals to Vs minus Vs2 divided by R. Okay, again, like R is very small and whatever the difference of voltage, so there will be some circulating current. Again, we don't want that. We don't want any circulating current, right? That is one problem. Now, even if you say that okay sir, that their voltage ratings are same. If you say that their voltage ratings are same, so this is VS1, VS2. So if voltage ratings are same, then of course their turns rating also will be same, right? So that's same thing. They must have same voltage rating. It is saying same thing as equal, like same turns rating. So these two things are same only, equal voltage ratio and saying that same voltage ratings, both are saying the same thing only. But equal voltage ratio will not always actually work. This, like this term is what, equals voltage ratio. If I take a example, let's say take that my supply actually is of 400 volts and output is, let's say, some 200 volts. Okay, so here, right, the turns ratio will be what, 2 for the first transformer. So the second transformer, if the supply, let's say it's rated, like its primary is 500 volts and its secondary is 250 volts, so this turns ratio is also same, 500 by 250. But will it work in parallel condition? No, because there is voltage difference between the primary, right? So just be careful that this, right, is bit flawed. Exact statement should be they should have same voltage rating. This is the correct condition. They must have same voltage rating. Okay, if they have same voltage rating, automatically the turns ratio will be same. Okay, so you should say this, they must have same voltage rating and they must have same polarity. So these two conditions are mandatory conditions. Now let's discuss about the desirable conditions. Okay, so now let's discuss about the leakage impedance thing. So there was a condition, third condition was about the leakage impedance. Why we want the leakage impedance to be equal? Okay, we will discuss about that. So if I see over here, that I have this V1 and V2, E2 voltage, all these things are here, right? All these voltages are here. Okay, so what I will do basically is that I want to see which transformer is delivering how much of current, because there will be some load sharing happening. Okay, we will see that. So these are the impedance ZA and ZB. So these, right, I can rewrite this whole equivalent circuit in terms of this. Okay, it will be easier for us to solve. What we have done is we have just drawn the secondary of this circuit. We have not drawn the primary, because ultimately secondary is here, right? E2 voltage is here, ZA is connected here, ZB is connected here, and the output is connected to V2. Okay, that is here. Okay, so now we want to see which transformer is delivering how much of power. Okay, so the kVA delivered by transformer A will be what? SA will be E2 into IA star. SB will be what? SB will be E2 into IB star. Okay, this is my SA and SB, right? Can I find out what will be this IA and IB? E2 is common, right, between these two. So if I just know the IA and IB, I will be able to find out the ratio of SA by SB. Okay. So, and now one more thing, what is the load KVA? Load KVA will be, it is V2 into V2 into IL star, correct? It is V2 into IL star. Or right, approximately what I can assumption is approximately V2 and that E2 are almost same. Okay, assumption is there is very low drop, so we assume that V2 and E2 are same. Okay, so assumption is this is almost equals to E2 into IL star, correct? So now how do I find out the load sharing? Okay, so IL, right? This current is IL, this current is IA IB. So you can use the current division rule, simple current division rule, right? So what will be the current? IA bar, IA bar will be basically IL into the opposite impedance ZB upon the sum of the impedance, that is ZA plus ZB. Okay, this will be my IA. Got it? What about I2? So what will be my IB? IB will be again IL into the opposite impedance, correct? Into the opposite impedance. So it will be ZA divided by ZA plus ZB. Okay. So this will be here, right? What I can comment now. So what will be the SA then? SA will be basically, it will be actually SL into ZB divided by ZA plus ZB. Or am I correct? Okay, so hold on. So right, this is equals to, so IB is this value. So if I replace here IB, what will I get? Or if I replace IA here, my SA will be equals to E2 into IB bar. So this will be basically, IB bar will be, this is ZB, so this ZB will still be here. Actually we should have actually mentioned this is magnitude, right? Or not magnitude. Yeah, this is fine only. This is fine only. Yeah, this will be bar only. That is fine. So now if I take the conjugate of this whole thing, this will be IL into ZB. So this number divided by ZA plus ZB. This is all, these are all complex numbers, right? Whole conjugate, correct? This whole conjugate. So this value will be what? This value here, SA will be this value. SA will be equals to E2 into IL conjugate. What is IL conjugate? E2 into IL conjugate is what? SL. So this will be SL only. This will be SL only into this value. So ZB bar conjugate divided by ZB bar conjugate divided by ZA bar conjugate plus ZB bar conjugate. Okay. So this is my SA. Same way SB will be SL into ZA bar conjugate divided by ZB bar conjugate plus ZA bar conjugate. Okay, same thing only, nothing will change here. So what is the ratio of the power apparent power kVA delivered by SA to SB? So this will be ZA star divided by ZB star. Like if I want to calculate the magnitude will not matter. I mean magnitude will be what, because ultimately I just want to find out the ratio, how much kVA they are sending, right? I don't care about the phase and all those things. So this will be SB bar will be equals to mod of ZA and mod of ZB. So basically it is mod of ZA divided by mod of ZB. Okay, so this is the ratio. So actually what is happening is that, okay, is it ZA? Sorry. This will be ZB by ZA. Sorry, ZB divided by ZD. So this will be ZB divided by ZA. So actually what is happening is they will deliver the power respect to their ratio, inverse of the leakage reactance. So basically the apparent power, the power delivered by a transformer will be inversely proportional to its leakage impedance. What is leakage impedance? Basically it is R plus Jx, right? That simple, winding resistance and the leakage reactance. That is what leakage impedance is, nothing else, right? Same thing. Okay, R plus Jx, that's it. Okay, got it? So yeah, that is the thing over here. I hope you have understood this point. Okay, so case 1, right? If both the leakage impedance are same, then what is the SA over SB? SA over SB, it is complex number. Okay, I forgot to write, it is a complex number, right? SA, SL, all these are complex numbers, so that's why a bar will be there. Here this will not be a complex number anymore, this will just be a magnitude. Okay, SB, and this will be SA, this is there, SL is there, SB is there, these are all complex numbers. Okay, so yeah, if both are equal, this will be SB into SA by SB, that will be equals to 1. If both of them are equal, this will be equals to 1, because the magnitude is equal, right? So then they are sharing the load equally. So basically magnitude of whatever apparent power delivered by the transformer A is same as the apparent power delivered by the transformer B. So basically what does it mean? It means that both are sharing the load equally. Okay, and here in case 2, if both of them are not equal, then they will obviously not share the load equally. If let's assume that ZA, magnitude of ZA is greater than magnitude of ZB, then what will happen? Basically in the same equation, my magnitude of SB will be greater than magnitude of SA. So basically the apparent power delivered by transformer B will be higher than the apparent power delivered by transformer A. So apparent power delivered by transformer A, by transformer B will be higher than transformer B A. Okay, so as they are inversely proportional, so if the leakage impedance of ZA will be higher than ZB, so transformer A will deliver transformer B will deliver more apparent power than transformer A. Okay, that is the basic funda here. Got it? Okay, so that's why we want them to have equal leakage impedance. If they have equal leakage impedance, so they will share equal load. If they have different leakage impedance, then they will share unequal load. So transformers So in this case, transformers share load unequally. So now what I want, actually I don't want this. Like, what is the problem here? Let's take few numbers. Okay, let's take few numbers. If I take this number, that let's say I have two transformers. Okay, like this, I have two transformers that are connected in parallel, and their leakage, this transformer is rated for 20 kVA or 30 kVA, let's say, and this transformer is rated for 60 kVA. Okay, now what is happening is, let's say the leakage impedance ZA, here it is 2, and the leakage impedance, let's keep it 3, and here let's keep it ZB equals to 2. And what kind of load they're supplying? They're supplying a load which takes around, let's assume, 20 kVA. Okay, so they're supplying 20 kVA. Now what will be the load sharing? So SA will transfer how much? SA will transfer basically ZB divided by ZA plus ZB whole magnitude, right? So ultimately, right, okay, this, okay, it is like, what is my SA divided by SB? It is inversely proportional, so this will be 2 divided by 3. Okay, and also I know that SA, magnitude of SA plus, okay, not this overall thing, but overall SA plus SB, right? SA plus SB will be 20 kVA, 20, right, 20 kVA. So from here I can directly say that SA will be 2 by 3, 2/3 of SB. So if I place it over there, this will be 5 by 3 of SB, magnitude of SB will be equals to 20. So SB will be actually equals to 12. What will be SA? SA will be only 8, right? Are you noticing anything weird? Are you noticing anything weird? Yes. So although the rating of this transformer is 30 kVA only, but this transformer is delivering 12 kVA, and the rating of this is 60 kVA, but this is delivering low power, 8 kVA only. But maybe this is not a good approach, right? This is not a good approach. Actually, what I want them to transfer the power proportional to them. Okay, proportional to their ratings actually. So how will I bring that into factor? I want them to always share this power proportional to their ratings, because if, let's say, I am delivering 60 kVA, so I would want, because the ratings are like, this is double, so this should deliver double the power. Okay, the rated power is double, so this should deliver double the power. So for 60, right, this one should deliver 40 kVA, and this one should deliver 20 kVA, because the rating is lower, right? Here rating is lower, that's why this one should deliver less power, this one should deliver more power. So I want their power delivery to be ratios in terms of rating. So basically what I want, so I want their power delivery magnitude of SA divided by magnitude of SB, ratings of their, so that is equals to ZB upon ZA, that we already have established. This I want them to be proportional to the ratings. So this one will be SAR magnitude divided by magnitude of SBR, the ratings of their KV rating basically of the transformers. Okay, so this will be basically now these two are equal, correct? If these two are equal, I can directly write here magnitude of SBR into magnitude of ZB equals to magnitude of SAR into magnitude of ZA. So basically what is happening, you remember one formula. Now I know that their voltage ratings are same. Their voltage ratings are same, right? Secondary and primary, their voltage, both these transformers voltage ratios are same. So if I divide on both sides by kV whole square, because their voltage ratings will be same, right? If I divide on both sides by kV whole square, so I'll copy this equation, paste it over here, Z base by kV whole square. Now is this something familiar to you? Is this something familiar to you? This is familiar, right? What is it? It is ZA upon Z base basically. This is the Z base of the transformer A. This is the Z base of the transformer B, because here I have rated kV of the transformer B. Here I have rated kV of the transformer A. So this will be ZBPU equals to ZAPU. So ultimately this is the actual condition. That's why if you see, remember here, right, what we discussed, the desirable, this is not a like mandatory condition, because if it is not satisfied, then also they will share the load, but not proportional to their rating. That is the only problem here. If you see that identical per unit impedance, okay, on their own MVA base for proper load sharing proportional to their rating. Now I hope this term, this sentence is clear, why they should share the load proportional to their rating. Okay, so that is the thing over here, that this, if this condition is satisfied, remember this per unit with is here, the base is with respect to transformer A, and here the base is with respect to transformer B. Okay, so now we have, I hope you understand that what is, why this condition needs to be satisfied. If this condition is satisfied, then load sharing will happen proportional to their rating. Okay, load sharing will happen proportional to their rating. So I hope you have understood, like whatever we have discussed, like why unequal impedance, what are the problems, overloading will happen, right? Here if you see, overloading was happening. I took the example right here, like initially this SB was delivering more power than this SA, but this has higher rating, right? So overloading is happening here in the transformer B, that I don't want. So same thing, whatever we have discussed is written here. Okay, so yeah, this was basically about the load sharing condition. And next condition is the basically the per unit impedance already we have discussed. So now let's come to this next condition, that is they must have same X by R ratio. Now it is not mandatory, but it is a desirable quantity. Why? If the X by R ratio is different, okay, if the X by R ratio is different, so if the X by R ratio is different, that means what? That basically means that, let's assume this is my IL current, okay, this will be equals to IA plus IB, and if my X by R of this transformer A and transformer B are different, that means my IL bar will be equals to IA IB bar theta A, magnitude of IB bar theta A plus magnitude of IB bar theta B. Okay, so now, right, what is the problem? The problem is it is not proportional to the magnitude actually. If it is not proportional, like my IL is not exactly proportional to magnitude, there will be problems, right? If they were equal, if theta A is equals to theta B, then I can directly comment this out, that my magnitude of IL will be equals to this whole thing, right? Because both are in same phase only, theta A and theta B. So it will be magnitude of IA plus magnitude of IB I can directly say this. Why? You can draw the phasor diagram. Okay, this is the reference. Let's assume if theta is not equal to theta b. So this is my theta a and this is my theta b. Okay. So what I can comment is that here, if they are not equal, so here, right, I cannot write this equation, and if I cannot write this equation, then I cannot say that, okay, this I need to delete, this was there previously. That means I cannot directly comment that they will share load proportional to their impedance, magnitude of impedance. If they are not equal, right, if theta a is not equal to theta b, that means I cannot comment that load will not be shared proportional to their leakage impedance, because it will not be proportional to the magnitude anymore, because the power factors will be different, then calculations also will be different. Okay, so it's a, like, then basically load sharing will not be equal, they will not be proportional, they will not be whatever we had derived in the previous condition. So to achieve that, we want x by r to be as close as possible, so that this magnitude condition is satisfied, so that they share proportional to their rating. Okay, this much only you need to know, nothing else. So another thing, if their x by r ratio is different, right, if their x by r ratio is different, then they will basically share, if x by r ratio is different, then the phase angle of the currents will be different, then there will be an what do you call, reactive power transfer between the transformers. So there will be reactive power transfer between transformers, which is not a good thing. Okay, that's why we want, like, it is a desired quantity to have the x by r same, but even if it's different, then also it will be fine, but desired parameter is their x by r must be same. Okay, so yeah, these are the conditions basically. So like we all already discussed it. So if one transformer fails in parallel setup, remaining all other must absorb the full load. So if we don't satisfy these conditions, then they will not be able to share the load properly. Okay, we have few protective measures as well, like protective relay, circuit breakers. All these isolate the faulty units. These are for power system analysis, we will not discuss here. Okay, and few theoretical points we are discussing, basically temperature rise and impact on parallel operation. So operating multiple transformer in parallel can lead to unequal loading, which we have already discussed, especially if impedance is mismatched. This affect heat distribution and may result in the damage, right? Basically, if a transformer is rated for 30 kVA, another one is rated for 60 kVA, I'm delivering a load of 40 kVA, but the 30 kVA transformer is actually loaded with 25 kVA, and the 60 kVA transformer is only loaded with 15 kVA. Okay, that is not a good thing. Like overall, I'm sharing 40 kVA, that is fine, but this is overloaded, this is underloaded. So of course, if it is overloaded, it will get damaged soon. More heat will be developed, it will get damaged soon. Okay, so that is what is written over here. There will be reduced efficiency, there will be insulation aging. All these are interview questions. So these all are interview questions. Okay, interviews, these can be asked. So we are covering everything. So that's why I am preparing you for interviews as well. Okay, so this is the thermal management strategies, and we have to ensure like adequate cooling is there, we have to monitor the temperature, all these things we have to do. So you can go through, read through this. Okay, so summary of parallel operation. So same polarity is a mandatory condition, equal voltage ratio and rating is a mandatory condition, this per unit impedance depending on their own base is a desirable condition. So this is we already know, this is like equivalent impedance is proportional to the kVA, and same x by a ratio. If they have same impedance angle, then their operation of power factor will be same, the theta angle will be same, then load will be also proportional. Okay, so what are the steps that someone needs to verify for proper parallel operation. Okay, this can be also asked in interview. First, we have to verify the voltage ratio and phase group. Phase group is for three-phase transformer, which we will discuss later on in the next lecture itself. Okay, you can ignore this for now. Then we have to calculate the per unit impedance. See if they are same or not, depending on the base. Okay, and then the simulation are there. Then we have to install protection devices and then perform the load sharing test. So these are the practical steps how you can basically ensure a proper parallel operation. Okay, now let's solve few questions. So I will give you this, like I will show you all the questions. You try it out by yourself, and I will try to solve all the questions. Okay, after you try it out by yourself. So yeah, these are all the questions basically. Now I will start. Okay, so this is the first question. So in the first question, two transformers T1 and T2 each rated at 500 kVA. So I have two transformers. Okay, this is the two transformers. So in short, right, we can draw the transformer like this. In a power system analysis, we will use this multiple times. So this will be 500 kVA transformer. Another transformer is in parallel, 500 kVA. Okay, so percentage impedance of T1 and T2 are 1 plus J6 and 0.8 plus J48 respectively. Okay, so percentage basically I guess they are talking about per unit impedance or something, or they are not talking about per unit impedance. Yeah, percentage impedance means per unit impedance only. So here the per unit impedance is 1 plus J6. Okay, 1%. Okay, remember it is 1%, it is 1%. Okay, so this will be in percentage. So this will be 0.01 plus J 0.06 pu of the transformer 1, and this will be 0. Okay, this is 0.008 plus J 0.048 pu to share a load of 1000 kVA. So I have a load of 1000 kVA. Okay, at 0.8 power factor lagging. So this is 0.8 power factor lagging. The total contribution of T2. What will be the total contribution of T2? How will I calculate it? Okay, so we can use our formula, right? What is the formula? Formula of S1 will be equals to what? S1 will be SL into the opposite impedance, that is Z2 divided by Z1 plus Z2. Right? If you remember, it was the opposite impedance. Correct? Okay. Z2 divided by Z1 plus Z2. Or what we can say, as they're delivering, right, 1000 kVA, so we can directly write this, that first thing is I know S1 divided by S2 will be magnitude of Z2 divided by magnitude of Z1. This we already know. Okay, and also I can observe that their X by R ratio is same. X by R ratio and X by R ratio here is same, so they will totally deliver according to their power factor only. There is no problem with that. Okay, so what I can write over here, S1 by S2 will be this value. So my S1 will be equals to or S1 by S2, if I write down the ratios, this will be magnitude of 0.101 whole square plus 0.06 whole square whole under root divided by magnitude of 0. Okay, this is not okay, sorry, this is Z1, right? Z1 should come below. 0.0008 whole square plus 0.048 whole square and this is here. So now if I calculate these values, right, what will be the value basically? One whole square plus 0.06. Okay, this is basically 0.002368 whole under root divided by, this will be 0.01 whole square plus 0.06 whole square. This will be 0.0037. Okay, so this into 0.002368, this comes out to be 0.64. If I take this whole under root, this will be 0.8 only. So this will be 0.8. Okay, so how much contribution will be from T2? What will be the contribution between T2? So S1 is equals to 0.8 S2, and I know that S1 plus S2, as X by R is same, then only I can apply this formula. Because I know X by R is same, then there will not be any power factor difference. So X1 by R1 is equals to X2 by R2. If I just write down the values as they are same, then there is no problem with this. I can simply apply this formula. Okay, okay, one more thing. Okay, one more thing I forgot to tell you, that in this case, right, because the kVA is same, so here I replace here ZPU. So this, right, if the kVA ratings are same, that means my Z1 base is equals to my Z2 base, correct? Why? The kV ratings are same, voltage ratios are same, so everything is same. That means the base ratings also will be same. So that's why I can divide and multiply by, let me write here ZB. So if I divide by ZB here, I forgot to mention that Z2 divided by ZB, and here magnitude of Z1 divided by ZB. So this will be basically Z2 PU divided by Z1 PU. Okay, Z2 PU divided by Z1 PU. So that's why I replaced here directly Z1 and Z2 PU, right? That's why, that is the reason. You cannot directly replace it. Actually, they were absolute values, but I divided by Z base because both are same here. Z base are same. Okay, because S1B is same, right? The ratings are same and voltage are anyway same. So that's why, remember, that's why I can do this simplification. Okay, otherwise you would not be able to do this. Remember this. Okay, got it? Okay, so my S1 plus S2 is equals to my SL only if this is true, right? That is, it will be equals to 1.8 S2 is equals to SL. What is SL? SL is 500. Okay, 500, sorry, not 500, 1000 kVA. 1000 kVA, right? What is the angle? Angle will not change because x1 by r1 is same. Angle is zero 0.8 power factor lagging, so it is minus 36.86, minus 36.86. Okay, I will not explain you this all conversion and all those things, right? Assumption is you already know all this. So 1000 divided by 1.8, so this will be S2 will come out to be 555.55 kVA. They have only asked us the magnitude, so it will be 555.55 kVA. They have not asked us the phase angle. Phase angle in this case will be minus 36.86 only. If this x by r ratio would not have been same, then the phase angle would have been different. I would have to solve the circuit. I would have to solve the circuit if this x by r was not same. Okay, that is the thing over here. So it will be 555.55. This will be your answer. So now let's discuss, before the next question, I want to discuss load sharing when the full load currents are given. How to optimize the load sharing without overloading. So load sharing without max, this is basically maximum load sharing. I will write here, it is basically maximum load sharing without overloading. What do I mean by it? So one thing I know is I have this transformers in parallel, transformer A and transformer B. These are my like the ratings. This is my impedance, leakage impedance, and this is my full load current. Full load current will be different. Why? Because the ratings are different. Voltage is same, but as the ratings are different, so full load current also will be different. Now, if they are connected in parallel, what can I comment? I can comment whatever the drop here, right? Because these two are same E2 potential, right? And this is same V2 potential. So whatever is the drop here, that is what? That is basically IA into ZA. That will be same as the drop here. That is IB into ZB. Okay. Same drop will happen here, here and here. Okay. So what I can do is I can directly say that what can I comment? What can I comment? So I can directly comment that this condition will always be true. IA into ZA will be equals to IB into ZB. Correct? Now what I am doing, I am increasing my load. So my load current is increasing. So if load current is increasing, I am increasing my load. So if my load current is increasing, so my IA also will increase. So my IB also will increase. Both of them will increase. But this relation always will be followed. This relation always will be followed. Now I don't know which one will come to rated condition first. I don't know that. I don't know which transformer will come to rated condition first. Okay, I mean which like what do I mean by overloading? Overloading means the current that is flowing through the transformer is more than full load current. So let's assume that the transformer 1 reaches full load condition first. Okay, assumption is transformer 1 is reaching full load condition first. That means what I will replace here with IA? I will replace IA with IAFL into ZA. What will be IB? IB will be IB only because, sorry, not transformer A, transformer 1, transformer A, right? Assumption is transformer A has reached full load first. That means transformer B is yet to reach full load. So this will be equals to IB into ZB. Okay. That is the case here. Correct? Very important, like very important condition. I will explain you just in a bit. So IAFL ZA equals to IB into ZB. So now what I can comment? What I can comment is that here, right? One thing is for sure that if I have reached here full load first and still I have time left to reach full load here, right? Still I have time because IB will increase, like my IB, whatever value of IB, because assumption is IB is has not, the transformer B has not reached full load yet. That means my IB, whatever the current, like whatever is the current right now, I will calculate for IB, that will be less than the IBFL. That's why it has not reached full load yet. So what I can conclude from here, I can do back calculation. What I can conclude, so this is IB is less than IBFL. So I can use the property of inequalities. So if IB is less than IBFL, that means if I multiply by ZB on both sides, okay, so IB into ZB will be less than IB into, sorry, IBFL into ZB. Now what I can do is I can replace IB into ZB by this value. What is IB into ZB? IAFL into ZA. So this will be IAFL into ZA will be less than IB FL into ZB. So this is a very important condition. Now I will do backtracking. What kind of backtracking? So if this condition is getting satisfied, that means what? That means my transformer A will reach full load first. I'm doing back calculation. Every engineer loves back calculation. Okay, so what I'm telling, that I started with the assumption is transformer A reaches the full load condition first. If transformer A reaches the full load condition first, that means this will always be satisfied no matter what, because they are in parallel, and this point is EA, E2, and this point is V2. So the drop will always be same no matter what. So that means I will write this equation. Then I will write that as transformer B has yet to reach full load, that means IBFL will be less than IB. If I multiply by this, this will be this. If I replace IB ZB with this, that means if this condition is getting satisfied, that means the transformer A will reach full load first. Okay, back calculation. So I will check how to check which transformer will be reaching full load first if I keep on increasing my load, if they have different full load currents. This is the condition. If the voltage drop across the transformer A is lower than the voltage drop across the transformer B, full load voltage drop. So these are called as the full load voltage drops. Full load voltage drops. Okay, that means basically that means then this will reach the full load first. That means whichever transformer will have lower full load voltage drop that will reach rated condition first. Of course, I cannot go beyond that. If I go beyond, if I keep on increasing my load, this right will increase. So I cannot go beyond my full load current. So then how will you find the like I2 current? How will you find the I2 current? So I2 current is very simple to find out, right? I2 current will be basically assumption is, how will you find out the other current? Other current is very simple, right? IB will be equals to IAFL ZA by ZB. That's it. IAFL ZA by ZB. Okay, very easy to find out. Not that difficult, I guess. Okay. So this thing I wanted to keep you in mind. So assumption is, let's take the assumption. Let's find out the equivalent values basically. So first thing is, if I have two transformers, so overall kVA of the load will always be equals to the kVA of the transformer A plus the kVA of the transformer B. No matter what, this will always be satisfied. Now, if we are searching for the maximum condition, right? Maximum. Okay. So if I am searching for the maximum condition, that is like I keep on increasing my kVA load, and where will, like, how will the transformers behave basically. So I cannot go beyond a certain level because one of the transformers will reach its rated condition. So if I assume like maximum load without overloading transformer. Okay, maximum load without overloading transformer. So this will be my kVA, whatever is the maximum load, equals to, let's assumption is the first transformer is reaching rated condition. So it will be kVA 1 rated condition plus I the second transformer. How will I find out the second transformer value? How will I find it out? So one thing I know is that the second, like, I know this condition will be satisfied. What is the condition? Condition is as transformer 1 is getting rated first, reaching rated condition first. So this will be I1 FL I1FL into what do you call I1FL into Z1 or okay, I'm talking about Z. Okay, let me write it in terms of A only, AB. So ZAR, so this will be IAFL into ZA will be equals to IB FL into ZB. Okay, and I know, no, not this, right? Because this is reaching first, so this will be the value right here, because IAFL ZA will be equals to IB. So from here I can actually find out the current of the transformer B at this condition, that is IAFL divide by IAFL into ZA upon ZB. Okay, this is my current basically. Now can I actually use something? Can I use something? I want to write this in terms of the S base. How will I write this in terms of the S base? Basically, that is what I am trying to figure out. Okay, so right, this is IAFL, that is fine. IAFL is fine. So if I divide by IBFL on both sides, if I divide by IBFL on both sides, what will I get? So this will be IB upon IBFL equals to IAFL divided by IBFL into ZA divided by ZB. Okay. Now what is this? What is, do you remember what is this? This is basically the fraction of loading. This is X, right? So how will I find out the kVA now? How much kVA is the transformer sending? It is X into kVA rating of the B. So this is the total amount of kVA that it is transferring. Correct? Very simple and easy to understand, right? IB upon IBFL, yeah, will be the X value, fractional loading. So basically this, right? This is my X. So X is this value. X is this value. Okay. So overall kVA, how much it is transferring? X into kVA rating of the rated kVA, right? X into rated kVA of the transformer B. Okay. This is X. X is what? Fractional loading. The current, I mean the current that the transformer is actually giving out divided by the full load current. That is known as fractional loading. We have learned this in the basics, right? Equals to, like this, I just manipulated the equation. That's it. Just have manipulated the equation. I have not done anything else. Okay. So here I will replace here, right? So overall kVA sent will be X into kVA of the B rated. So this will be basically X into kVA B rated. X is this value. X will be this value, that is IAFL. Don't worry if you don't remember the formulas. I am telling you how to derive the formulas, so that in the exam hall you can do the same thing. So IAFL divided by IBFL into ZA upon ZB. So this is my X value and into the kVA base, obviously kVA rating of B. Now this happens, this is the formula. Like, I don't want you to remember the formula, I want you to remember the concept. This will not always be valid, right? This will be valid only if the transformer A reaches full load first. That is my this is valid only when my IFLA into ZA is less than IFLB into ZB. Okay. Now this I can flip the formula. What I can do, I can simply flip the formula. So if my transformer B this time reaches the saturation, I mean not the saturation, the rated condition first. So that means what? This will be flipped simply. So this will be greater than. So transformer B will now reach rated condition first. So full load condition first. So what will happen now? So basically this will be kVA BR, because it will supply the rated power. Okay, I should not delete it. I should just change this sign here. So now kVA AR will not, like the transformer A will not supply the rated kVA. It will be a fractional loading. What will be here? Here, right? You can derive the formula. It will be IBFL divided by IFL. That's it. that is the only change, into kVA AR, and plus sign will be there with the kVA BR, because the B transformer will send rated kVA. Okay, that is the case over here. Got it? So 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 if I have three transformers, let's say, if I have three transformers, then what will be the formula? If for three transformers, if I have this was for two transformers, let's say I have three transformers. Okay, same derivation is there. So then again, assumption is one will reach the rated condition first. Assumption is, let's assume KV, like the first transformer reaches rated condition first. So assumption is, let's write this down. IFL1 into ZA will be less than the minimum of whichever one there is, IFL2 into Z. So basically, I can write it like this. So minimum of IFL A into ZA, comma IFL B into ZB, comma IFL C into ZC is equals to the transformer A only, because it reaches the rated condition first. IFL A into ZA. Okay. So what will be the maximum kVA that I can transfer without overloading any of the transformers? So of course, if this is the minimum, that means transformer A is reaching the rated condition first. So kVA by the transformer A will be kVAR simply. Okay. What about the other one? Again, same loading factor, right? Here it will come IFL A rated condition, full load current, divided by the IFL B for the transformer B into basically ZA upon ZB. Correct? Here as well, ZA upon ZB. Okay. This should be okay. This should be ZB upon ZA, right? I missed the point. This should be ZB upon ZA. You can derive the formula. This should be ZB upon ZA. ZB upon ZB. Basically, it is the full load drop, right? Full load drop. That's it. Simply, it is the full load drop. Okay. So this will be ZA upon ZB into the kVA of the kVA B rated. Okay. Plus IFL A divided by IFL C into ZA divided by ZC into kVA CR. Okay, got it? So this is how for a three transformer you can derive the formula. I just give you example. If this is the case, if this is satisfying, right? Remember, this has to satisfy, then only this formula will be applicable, else this will not be applicable. That's why understanding the concept behind every formula is very, very important. So now let's come to this problem. So two single phase transformer are rated this and this. Unit leakage impedance is given at this and this on their own base. So these are unit leakage impedance. Okay. So these are not actually the overall impedance, right? These are unit leakage impedance. So either you find out the per unit values, voltage, or either you directly find out the absolute values, any one. So here as they have given per unit, so I will convert my full load current to per unit as well. I will convert my full load current to per unit as well. Okay, that is the only difference that you will go. So all this will be valid if I just write in terms of per unit. It will totally be valid if I write this whole equation in terms of per unit. Okay, got it? Okay, so right, yeah, yeah, because here I previously did not mention you, because this will be valid for per unit as well. Why this will be valid for per unit? Can you tell me why this will be valid for per unit? So this is just a voltage drop, right? This is just a voltage drop, correct? If this is a voltage drop, what is the base of the voltage drop? It is VB, and voltage ratings are same for both the transformers. If transformers are operating in parallel, voltage drops will be same. So that's why if I divide this by VB, right, it will not make any difference. So if I divide this is what IFL A ZA is greater than IFL B ZB. If I divide this by ZB, Z base, not Z base, sorry, V base and V base. Why can I divide both by V base? Because why? Because the voltage ratios are same. Voltages are same. For what? For parallel transformer. Okay, for parallel transformer. Okay, so that's why this can be written as the what? The per unit drop, full load per unit drop of A, and like this can be written as full load per unit drop of A, and this can be written as full load per unit drop. I know it's a bit messy, but just bear with me. Full load per unit drop of B. Okay, so we can compare the full load per unit drop as well. There is no problem with that. Okay, so I will come back here. So we can directly write. So let us calculate. What are they asking? What is the maximum total kVA that can be supplied by two transformers operating in parallel without causing either transformer to exceed its rated capacity? So for that, how will I know which transformer will reach the rated capacity first? So for that, I will calculate the per unit full load per unit drop. So if I find out, so IFL1 in per unit will be what? IFL1 in per unit will be 1 pu, basically full load, right? 1 pu. IFL2 will be also 1 pu. What is the impedance? Z APU, transformer 1 impedance. Z APU is 0.02 plus J 0.06. So what is the drop here? If I want to calculate what is the drop here, so overall drop here, if I see IFL1 into Z APU, it is coming out to be 0.02 plus J 0.06, which is equals to, if I want to calculate here, right, the magnitude basically 0.02 whole square, 0.02 whole square plus 0.06 whole square whole under root, this will be 0.0634. okay, 0.0634. okay, so if I find out the angle as well, so 0.06 divided by 0.02 tan inverse, so this will be 71.56 degrees. okay, so and what about this, so this will be basically what is the per unit impedance of the transformer B? So it is 0.025 plus J 0.08. So this will be 0.08 whole square plus 0.025 whole square whole under root. So this will be 0.0838. So of course this is lower. Okay, here, right, I think I missed a point actually. Yeah, I missed a point. I will just quickly write, just hold on, 0.08 divided by 0.025 tan inverse. So this will be 72.65 degrees, and here, right, I missed a point here, I guess. I'll just quickly verify it again. I guess I missed a point. So these angles are almost same. okay, this is 0.02 whole square plus 0.06 whole square whole under root. Yeah, I missed a point. Yeah, sorry. So this will be 0. So which one is greater? So I see ZB, I mean which drop is greater? So I see basically my IFL, this is not 2 actually, sorry, IFL B and IFL A, right? So my IFL B into ZB PU, this PU, right, overall PU drop is greater than my IFL A into ZA PU. So which one will reach the rated condition first? So my transformer A will reach the rated condition first because it has the least drop, right? So hence we can conclude that transformer A will reach rated condition first. Okay, so if transformer A reaches the rated condition, so what will be the overall, because they have asked uh, how much kVA can, how much maximum kVA can I transfer, so this will be kVA total will be equals to the kVA of the transformer A at the rated condition plus this will be IFL1 IFLA divided by IFLB into Z A upon ZB, right? So this can be also converted in per unit. Okay, I have already told you this is voltage drop, this is voltage drop, so this can be automatically converted into per unit, no problem, because there is only ratio, right? And these are all voltage drop. If I divide by V base, it will be per unit only. So if it is valid for absolute value and for per unit both, it is valid for absolute value and for per unit both. Okay, into kVA BR. Okay, so this value, so my kVA T kVAR is how much? kVAR is this is the transformer A, right? 1000 kVA. So this will be 1000 kVA plus this per unit drops, right? So what is the ratio of the per unit drop? So this drop upon this drop, so this will be 0 0.0634, 0 0.0634 divided by 0 0.0838. Okay, 0 0.0838 into the kVA base of the transformer B, that is 500 kVA. Okay, so this value will be what? I will calculate this value. So this divided by 0 0.0838 into 500 plus 1000. So maximum what I can transfer is 1377. I cannot go beyond this. If I go beyond this, then the transformer A will go beyond its rated capacity, that will harm the device. Okay, just be careful about that. So this is the maximum. All this I have explained, concept I have explained, I have done the question. Okay, now let's solve this next question. So two more questions are left. Okay, three more questions are left actually. Three more questions are left. These are not that difficult. So three single phase transformers rated at 400 kVA, this 11 kV, 6.6 kV, 50 Hz were tested at rated currents. Okay, uh, with their low voltage winding short circuited. Okay, the short circuit tests were this. Okay, so their low voltage windings were short circuited. Okay, all the transformers are connected in parallel. Their primary voltage is maintained at 11 kV. What is the maximum load at unity power factor that can be applied to the parallel combination without overloading any individual transformer? Okay, so actually what we are doing, we are performing the short circuit test, right? And these are what? These are the voltage drop. These are the voltage drop when rated current is flowing, right? Short circuit test means what? Short circuit test means I equals to IFL. So voltage drop when rated current is flowing. So what are these? These are basically the IFL into Z1 ZA. Okay, IFLA into ZA. This drop is IFLA into ZA. This drop is IFL B into ZB, and this drop is IFL C into ZC. Okay, as simple as that. So they are asking me the maximum load that I can deliver at unity power factor. Unity power factor means kVA is same as kilowatt. Okay, so I can directly find out, so which one will be in rated condition first? This transformer. So T1 will be in rated condition first. Okay, so because they have written here T1, T2, T3, so we'll write here 1 2 3, 1 2 3. Okay, so this is the lowest value. So I can safely say that T1 will reach rated condition first. So these kind of questions will come. Okay, very good question. Rated condition will reach rated condition first. Okay, so if T1 reaches rated condition first, that means what will be the overall kVA rating? Total kVA rating will be basically T1 has reached rated condition. What is the kVA rating of T1? They've given me T1 has 400 kVA rating, right? Okay, 3 transformers are rated at 400 kVA only. So this will be rated at 400 kVA only. So 400 kVA it will be plus the second transformer. For second transformer it will be the drop of the first transformer, that is 360, divided by the drop of the second transformer, right? So 360 divided by 400 into the kVA rating of the second transformer, which is same, all the transformers are identical. So this will be 400 kVA plus then again drop of the first transformer divided by the drop of the third transformer, that is 480. So this will be 480 into the kVA rating, that is identical 400. So this will come out to be 9 divided by 10. So this is like 36. Sorry, 360 only. Oh, okay. This is 360 only, plus 360 plus this will be how much? This will be 480 into 360 into 400. So this will be 300 only. So this will be 700 1060 kVA. Okay, so this value will be 1060 kVA. This is the maximum amount of kVA that I can transfer, because they have asked the power. So as it is unity power factor, so it is same, right? kVA is same as like your kilowatt will be what? kVA cos phi, right? kVA cos phi. So kVA is cos phi is 1, it is unity power factor, so it will be 1060 kilowatt. Okay, so here 1060, it is not kVA actually, the maximum power they have asked actually it should be kilowatt. Okay, this question should have been changed to kilowatt, but that's fine. Okay, I hope you get the point. That is the important point. You get the point, right? So yeah, let's solve this question. The second part tells us that what will be the secondary terminal voltage under the above rated condition. Okay, under this operating condition, what will be the secondary terminal voltage? So for that, I have to use the formula of voltage regulation. What is the formula of voltage regulation? If you remember, the formula of voltage regulation was basically percentage voltage regulation. If you remember, it was I R cos phi plus I x sin phi, right? This was the percentage voltage regulation into 100%, of course, was there, right? Divided by voltage was also there, if you remember, divided by the this no load voltage, that is the E2, right? Divided by E2, that is 6.6 in our case, correct? If you remember this formula. Okay, so any one transformer works, because transformer, I know transformer 1 is in the rated condition, so I will choose the transformer 1, because what is happening, because all the three are basically in parallel only. So here this is the transformer 1, this is the transformer 2, and this is the transformer 3. Okay, so all of the three transformers are actually in parallel only, right? If they're in parallel, so it does not matter, the voltage drop will be same, right? Voltage drop will be same, right? Whichever one I find out, it does not matter actually. Ultimately the voltage drop will be same. So I know this condition, I know this transformer is in rated condition, so I know the current, I can find out the current from here, right? So this will be easier for me to solve. Okay, so this, if you remember, this was actually not only R, this was RO2 equivalent impedance and XO2. So I know my what I know my cos phi is actually 1, because it is operating in unity power factor. They have mentioned it is operating in unity power factor. Okay, and my sin phi is 0. So ultimately the expression for voltage regulation comes out to be IFL, because it is a full load current, into RO2 cos phi is 1 divided by E2 no load basically. So this is what this is basically, if you remember this formula, into 100 was there also, into 100 was there also. Okay, if I want to discuss, because they are asking me the terminal voltage, I have to find out the terminal voltage. So let me keep it as it is, let me keep it as it is only, let me not go to the this per unit value, let me not go to the per unit value. So what is IFL1? How do I find out IFL1? So I know the kV rating of the transformer, I know the secondary voltage, so I can easily find out the IFL1. So it will be, kV rating is 400 kV, right? Yeah, 400 kVA divided by the secondary voltage, that is 6.6 kV, right? 6.6 kilovolts. So this value, right, IFL1 will come out to be what value? So IFL1, this will be 400 divided by 6.6, so this will be 60.61 amperes. Okay, so that is my IFL1. What is my RO2? Do I know my RO2? So I know my full load copper loss. I know my full load copper loss. What is this equals to? This is basically IFL1 whole square into RO2, right? This is my full load copper loss. Very simple. So from here, I can directly find out the value of RO2. So RO2 will be equals to what? This will be 3025 divided by IFL whole square, that is 60.61 whole square. So this will be basically 0.8235 ohms. This will be the value of RO2. Okay, I know RO2, I know IFL1, I can simply find out the percentage voltage regulation. What is the percentage voltage regulation? If you remember, the percentage voltage regulation was E2 minus V2 full load, that is a no load voltage minus full load voltage divided by the no load voltage, E2 no load. Okay, because they are asking me the terminal voltage, so actually I will not use this percentage formula, I will use this formula only. So what is IFL1 into RO1, RO2? So this, right, this will be here only. So from here actually the E2 no load cancels out, so E2 no load will simply cancel out. Okay, so I can directly write down the V2 value. So what will be the V2 full load value? V2 full load value will be E2, that is 6.6 kV minus IFL1, that is 60.6 ampere, into the RO2. RO2 is what? RO2 is 0.8235, 0.8235 ohms. Okay, so from here I can easily find out the no load terminal voltage. So into 60.6, okay, 49 plus 6600, so this will be 6550 volts. This will be my V2 full load. Okay, so from here you can directly say like what will be what is the terminal voltage under this condition? It will be option C, that is 6550. Anyways, from the option also you can see that this is not possible. Terminal voltage cannot go higher, right? It is in unity power factor, it cannot go higher, so it cannot be equals as well. There will be some voltage drop, either it will be this or none of this. Okay, so none of this was also present, so that's why you had to calculate, that's why you had to calculate basically. Okay, now let's solve the final question of today's lecture and we will be totally done. It's like night of 1:50 p.m. right now, I mean night of 1:50 a.m. Okay, because just I'm in the flow and I cannot stop the recording, I have to record, and next day I have to go into office as well. So you just don't know what kind of effort goes in here. Okay, so let's solve this. Two single phase transformer with voltage rating this and this have power ratings this. Okay, so TA is equals to 200 kVA and TB is equals to 100 kVA. Okay, the 200 kVA transformer has an equivalent resistance of 1 ohm. So okay, so equivalent resistance, so RA is 1 ohms and equivalent reactance XA of 5 ohms. Both refer to high voltage side. So this is I can write this is RO1A and XO1A. Okay, and the 100 kVA transformer has an equivalent reactance of 9 ohm, has an equivalent reactance. Okay, they have not discussed about the resistance. Okay, XO1 B refer to the primary is this. Okay, uh, okay, 9 ohms. Now what are the thing? What should be the equivalent resistance of 100 kVA transformer so that both transformers share load in proportional to their kVA ratings? I want them to share proportional to the kVA ratings. What should be the RO1B value? So if you remember, we had this condition, right? What was the condition? Condition was, if I want them to share, like what is the sharing condition? It was SA upon SB was equals to the ZB inversely proportional, right? ZB upon ZA. I want, now they are asking me they should share proportional to their kVA ratings. So this should be equals to SRA divided by SRB. So from here I can find out the condition. So what is ZB? ZB is basically RO1B RO1B whole square plus XO1B whole square whole under root divided by this, right? ZA magnitude. So what is ZA magnitude? It is 1 square plus 5 square. So it is under root 1 square plus 5 square. This will be equals to SRA. SRA is how much? Uh, SRA is this 200 kVA divided by 100 kVA. Okay, so this value I know what is XO1B. XO1B is 9 ohms only. So if I square on both sides, this will be RO1 B whole square plus 81. This is equals to 4 into 26. Okay, so from here I can directly find out what will be the value. So 4 into 26 minus 81 under root. So this will RO1B R1B is 4.79 ohms. Okay, 796 ohms. Okay, this has to match, this value has to match, then only they will share the load proportional. So this will be the first answer of the first part. Next part, what are they asking? What is the maximum total kVA that can be delivered by the two transformers operating in parallel without overloading? Again the same thing we have to apply. We have to find out the drop basically. So there are two transformers, so I will find out IFL1 into Z, IFLA into ZA. What is this value? IFLA, how much is IFLA? IFLA, right? Here if I write what is IFLA, IFLA will be 200 kV upon primary. If I just write down the primary voltage is 11 kV, right? So 200 upon 11. Okay, so it will be 200 upon 11 into ZA. What is ZA? So ZA value I don't know. Okay, ZA value is under root 26. So it is under root 26. So into 5.1 basically. So this value, right, into 200 divided by 11. This value is 92.7 volts. Okay, 0.71 volts. What about IFLB into ZB? So this value will be what? This value will be again, right, the kVA in this case is 100 kVA only. Okay, divided by the voltage. So 100 kVA divided by 11 kilovolt into what is the ZB. So ZB, right, ZB will be I guess it will be twice of the initial. If you just find out, right, it will be twice actually. So 4.796 whole square plus 81 under root. So yeah, it is 10.2. So it is just almost twice, 10.2. Okay, almost twice. So seems like, okay, both the drops are same only. Both the drops are same only. Okay. So if both the drops are same, so there does not need to be any worry. Both the drops are same. So both will both are actually sharing load in proportionally. So both will be in the rated condition only. Both will be in the rated condition only. I will prove it to you as well. Okay. So this value also will be 92.7. So actually what is happening is both are equal. So here what is happening? Both full load voltage drop are equal, hence both will operate in rated condition. Both will operate in rated condition. I can prove it to you as well. Operate okay. So what I can comment here is that if I use the formula, that is, let's assume that if you don't believe in me, right, you say no sir, you say that okay, transformer A is operating in rated condition, transformer B is not operating in rated condition. Use the formula. So kVA total is what? Transformer A, kVA AR, correct, plus into the loading. What is it? It is the voltage drop in the uh, transformer A, ZA, divided by the voltage drop in the transformer B into the kVA BR. Are you observing something? Are you observing something? So here these two drops are same. These two drops are same here, right? These two are same only. So automatically it is kVAR only. So even if you don't believe me, still you will write the same value. Okay. So this will be kVAR plus kVBR. So the kVAR is how much? The rated kVA of transformer A, it is 200 kVA. So this will be 200 kVA plus the kVBR. kVBR is 100 kVA. Okay, we see here it is 100 kVA. So this will be 100 kVA. So this will be 300 kVA. This will be the answer of the question. So 300 kVA will be the answer of the question. And for the question 2, so question 2 will be 300 kVA. This will be the answer for question 2. Okay, and this was the answer for question 1. Okay, I hope you have enjoyed this lecture. Trust me, you see anywhere in the whole gate industry, most of the teachers will not even explain you this maximum kVA total kVA rating, right? They will not even explain this. They will not even solve the questions. Okay, and even if they do, they will not explain the logic behind this. Okay, you go anywhere else you go, they will never explain this logic, whatever I have derived here, right? How is it happening? How have I assumed? Nowhere. You will find this nowhere. Trust me. You look anywhere else in the gate whole videos, you will not find this concept logic anywhere else. Okay, after this people will copy, I know, but you will not find it. Now if you see, you will not find it anywhere else. Okay, so all this we have to think as well. It's not like we're coming here directly writing just the formulas. We have to think, how can I explain it better? Okay, so yeah, if you enjoyed this lecture, so please, that's a request, please go into the first video of the playlist. Please do comment here. That will help us really out. Okay, so, and make sure to like the videos so that it keeps us motivated. I will see you in the next lecture. Until then, happy learning.